Today we're going to be talking about the Bitonic Sort algorithm, a fascinating parallel sorting technique that's like that incredibly talented musician who never quite made it mainstream, but absolutely dominates when given the right stage. Bitonic Sort has some unique properties that make it particularly interesting for parallel computing environments. We'll explore its history, understand how it works, analyze its complexity, and see why it shines in parallel settings despite being overlooked in everyday programming. In 1968, Ken Batcher introduced Bitonic Sort in his paper, Sorting Networks and Their Applications. It's difficult to find out exactly why Ken Batcher was working on this paper, but some insights can be gleaned from reading it. It's shown that Batcher was very focused on the hardware applications of the algorithm. Within the paper, two algorithms were mentioned, even and odd sort, and the superstar of this video, Bitonic Sort. The algorithm he developed was elegant, but quirky. Bitonic Sort has a very particular personality. It only works with datasets that are a power of 2 in size. Give it 7 elements or 13 elements, and it gets confused. But give it exactly 8 or 16 or 124 elements, and it performs beautifully. This pigginess, along with competition from more flexible algorithms like quicksort and merge sort, has kept Bitonic Sort somewhat niche. However, it has found its home in specialized applications, particularly in GPU programming, FPGA implementations, and other hardware-accelerated environments where its parallel nature really shines. Bitonic Sort is built around the concept of bitonic sequences. Sequences that first increase and then decrease. Or just increase, or just decrease. Think of it like climbing a mountain. You go up, reach a peak, then climb down. But a mountain could also just be a slope going down, or a slope going up. The algorithm works like two kids in a trench coat. There's the main Bitonic Sort function, and its friend Bitonic Merge. Each has a specific job, and together they create something more powerful than either could alone. Here's how the process works. First, the Bitonic Sort function recursively divides the array in half. Second, once the Bitonic Sort function hits its base case, it returns up and uses the Bitonic Merge function. The Bitonic Merge function then remerges the numbers according to the direction they were assigned. Let's take a look at the algorithm more formally. The input to the Bitonic Sort function should be an unsorted set of integers of size 2 to the n, where n is a natural number. And the output, a sorted set of integers of size 2 to the n, where n is a natural number. The recursive structure can be expressed as where m equals a plus b divided by 2, of course. Now let's see the pseudocode. These two functions here are Bitonic Sort and Bitonic Merge. First, Bitonic Sort wants to divide the array into two halves, one low half of the initial index to the middle index, and one upper half of the middle index to the ending index. While it is doing this, as it recurses down, it labels each half as either increasing or decreasing. Increasing in this case is 1, and decreasing in this case is 0. It does this till it reaches its base case, which happens to be 1 element. This is where the partner in crime, Bitonic Merge, jumps into action. Bitonic Merge functions a lot like Bitonic Sort. It also wants to recurse down through the array by slowly dividing it till it hits a base case of 1, but it also has another goal in mind. Each level, it looks at the direction and it tries to apply a swap to make sure that the numbers follow the sequence. It does this by checking at an index I and the index I plus k. In doing this, it checks if it follows the ordering. If it doesn't, then it swaps the two. Now here's the trick. You might think that one swap may be needed, or one run through, but that actually isn't the case. We can sometimes run into situations where more swaps are needed. This is why we recursively dive down into each half of the list and make it follow the direction of the superset. Let's analyze the performance of Bitonic Sort when running on a single processor. For the merge operation, we need to examine how much work is done at each level. The Bitonic merge function has this recurrence relation. The n over 2 term represents the comparison loop that runs across the middle of the sequence. Using the master theorem with a equal 2, b equal 2, and d equal 1, we get log b, a equals log 2, 2, which equals 1. And since d is equal to log b of a equal 1, we're in case 2. Now if you have the master theorem table up in front of you, then you should know what case 2 is. But if you don't, I will provide it on screen. Therefore, g of n is equal to n log n. Now, for a complete Bitonic sort algorithm, substituting our merge complexity in, we get this new recurrence relation. Solving this new recurrence relation gives us t of n equals n log n squared. This is slower than optimal comparison-based algorithms like merge sort or heap sort, which achieve n log n time complexity. However, this extra logarithmic factor is the price we pay for the algorithm's excellent parallel properties. Here's where Bitonic sort really begins to shine. The algorithm structure makes it exceptionally well suited for parallel execution. The key insight is in the Bitonic merge function. Look at this loop. I'll give you a second to see if you can see where we can optimize this with parallel processing. Every comparison in this loop is independent. We're comparing A0 with AK and A1 with AK plus 1, and so on. Since none of these comparisons depend on each other, we can perform all of them simultaneously with theta n processors. This transforms our merge complexity from 2. The comparison step now takes constant time instead of linear time. This gives us a new time complexity of theta log n for the complete parallel algorithm. Now, if we solve this recurrence relation, we get log n squared. This is dramatically faster than the sequential version, and faster than the parallel versions of most other sorting algorithms. And the catch? We need theta n processors to achieve this performance, one for each comparison operation. Bitonic Sort presents a very interesting and complicated trade-off in algorithm design. In theory, its parallel performance is outstanding. It's log n squared. I mean, that is amazing when compared to other sorting algorithms. But that is only when it has sufficient processors. In practice, there are several factors that limit the algorithm and its adoption. The elephant in the room, and probably the most obvious limiting factor, is that the algorithm needs O of n processors for optimal performance. Most systems aren't going to have processors that scale linearly with data size, and if we really think about this, most data sets that you're probably going to be sorting in the field are gonna be pretty large, and that is a big limiting factor, because if you have a data set that's over 1 million, you're probably not going to have like 500,000 processors or more. So it's kind of an unrealistic standard that the algorithm expects. Another really big limitation of this algorithm is the power of 2 restriction. Real-world datasets are rarely in perfect powers of 2. You either need to pad it with dummy data or use a different algorithm entirely. And furthermore, the implementation for Bitonic Sort is relatively complicated compared to other sorting algorithms. You have to have an understanding of what a Bitonic sequence is, and to even get its parallel processing to maximize its efficiency, that takes a lot more effort than using something like merge sort or heap sort, or even like quick sort. Bitonic Sort is a specialized tool that is incredibly powerful when you have the perfect storm of circumstances. But for general purpose sorting, it falls short of what you would want out of an algorithm. It's like a Formula One race car. It is phenomenally fast with the right track, right conditions, right driver, with everything in its favor in the perfect place. But you probably wouldn't want to use it for your daily commute. Like, if you're driving to the office, you probably don't want the Formula One. If you're driving out to see the grandkids, you probably don't want the Formula One. If you're driving for a vacation, you probably don't want the Formula One. It's just not suited for most cases. Showcasing algorithms in computer science is important. Sometimes you can find the best or greatest solution to a problem, but the solution isn't the most practical one. Bitonic Sort's theta log n squared parallel complexity is theoretically like the biggest kid on the block. It destroys the alternatives. But because of the demanding resources to achieve this performance, its applications in the real world are very constrained. All that being said, Still, understanding Bitonic Sort provides valuable insights into algorithm design, sorting networks, and the trade-offs between theoretical optimability and practical utility is important. In specialized high-performance computing environments where everything aligns with the exact use case of Bitonic Sort, Bitonic Sort still remains a elegant, beautifully crafted, powerful solution to any 2 to the power of n dataset that shows up. For the curious programmer, Bitonic Sort represents both the promise and the challenge of parallel computing. It shows us what's possible when we can harness massive parallelism, while reminding us that ultimately most real-world systems can't follow those constraints. Like Icarus, it flew too close to the sun and fell.